Hello. In this video, I will be solving two exercises from section 14.5 of James Stewart's calculus, and they're both on the chain rule. So the first problem we'll do is to use the chain rule to find dz dt or dw dt. In our case, it'll be dz dt because we have a z here, and we need to use the chain rule to find this derivative. So they give z as a function of x and y, and then they give x as a function of t and y as a function of t. In the next part, we're going to use the chain rule to find partial z with respect to x and partial z with respect to t. And here z is given by sine theta over r, where r is a function of s and t, and theta is also a function of s and t. Okay, so before I begin, let me remind us, or actually, let me backtrack. Some of you might notice that there are two different types of partial derivatives that we'll be computing with the chain rule here. So here, if we plug in x and y for x and y, we can see that z will be a function of a single variable t, hence we have the dz dt here. But in the next problem, we have z as a function of theta and r, but each of these depend on both s and t, and so we need to compute two separate partial derivatives. And the reason I'm mentioning this is because there's two different versions of the chain rule that apply for these different situations where we need to find an ordinary derivative or partial derivatives. Although they look very similar, and it's not too hard to just kind of guess what one looks like when you memorize what the other looks like, but we'll get to that in just a sec. So first, let me remind us of what the chain rule says for the univariate case. So if z is f of x, y, and x equals f of t, y equals g of t, give me a sec, equals g of t, then we can compute the derivative of z with respect to t, again, because it's a function of t when we plug in x and y. We can compute it as follows. dz dt is given by partial z with respect to x. So this is the partial derivative of z with respect to the x variable, times the derivative of x with respect to t. And note that here, I'm using just the normal derivative, not a partial derivative, because x just depends on t. And oh my goodness, I just realized this is probably bad notation. Let me change that to an h, because I'm already using f right here. But okay. And then up next, we need to do the same thing, but now we replace x with y, not partial, and then it's dy dt. And in general, if there were more than one variable, like let's say there was 3, for example, the derivative formula would be the same, except that we need to do this thing up here, but we need to add on the corresponding term for, I guess I should make this a different variable now, u. We need to add on the other variable for z, which would be ... just copying everything up here, and then partial u with respect to z times dz dt. I find a nice way to memorize this rule, or at least help memorize it, is that basically what we're doing is we're taking dz dt and we are basically multiplying and dividing by quote unquote dx, and then doing the same with dy. So like you might think of this as a mnemonic. dz dt equals, and I'll put this in quotes because, well, obviously this isn't the chain rule, but it helps to memorize how we're going to calculate these derivatives here. This is partial z with respect to x times dx dt, where here, you just multiply and divide by the corresponding dx. And again, in quotes, partial z with respect to y times dy dt, where now it's the dy's that have canceled. And what we're going to do is we're going to add these up at the end. To get our usual chain rule here. Okay, so marching forward, let's now actually calculate this derivative. So first thing we need to compute partial z with respect to x times, cancel out the dx here if you want to think of it that way, dx dt. Well, this will be partial z with respect to x is, what is this? This will be 1 over 2 root 1 plus x times y multiplied by the derivative of the inside with respect to x, which is just y. And then we're multiplying by dx dt, which here it's going to be secant squared t. Now we do the same. We just replace x with y. Partial z with respect to y times dy dt. Well, it's not hard to see that the partial derivative with respect to y will be exactly the same thing, but now we're just switching y with x. And then dy dt will be 1 over 1 plus t squared. And so then, adding up, dz dt will be this plus the same quantity but with x's replaced with y's, which is equal to y over 2 root 1 plus xy secant squared t plus x over 2 root 1 plus xy times 1 over 1 plus t squared. And if we wanted to, we could plug in the y and the x into these variables here to make the whole thing a function of t. But for my students, in my 2D discussion right now, I should point out that on some of your web-assigned homeworks, you won't need to go that far and plug in the expressions for x and y to make them in terms of t again. With some of the problems, the answers will be perfectly acceptable to WebAssign if you just leave them in terms of x and y, just making sure to include the derivatives with respect to t for your x and y functions. But you don't need to switch these partial derivatives into things in terms of t. And so this would be our final answer at that point. Now, let's move on to the next bits, where now we get a slightly trickier example because now we have to think of plugging in functions with two variables now. So it's very similar, and here the canceling of the partials is actually more apparent because we are using partial derivatives. So again, as in mnemonic, or actually, let me write out the chain rule first for two variables. Chain rule, this says that partial z with respect to s will be partial z with respect to, let's suppose z is a function of x and y. Then, oh wait, x equals, okay, so here x and y are both functions of s and t, just to not have to write all that. What we do is entirely analogous to the case where our functions x and y only depend on one variable, but now we're just taking partial derivatives instead. And we repeat the same with y. And that gives us the partial derivative with respect to s. Oh, that's not a times. That's not a plus. That's supposed to be a times. And it's the same story when you want to calculate the derivative with respect to t. Partial x with respect to t plus partial z with respect to y, partial y with respect to t. So again, notice how what I'm doing is I'm taking the partial derivative I want, and in quotes, I'm just multiplying and dividing by the intermediate functions. So here, actually, let me not use x. Let me use r and theta instead, because those are our intermediate functions here. I'm just multiplying and dividing by partial r, partial s, and then, or theta, sorry. And then I am, well, they cancel out. And I'm using this equality only as a mnemonic to help you remember how to calculate the partial derivatives for using the chain rule. Again, once we finish, we're going to add up, and that's going to give us our actual partial derivative. So, okay, let's compute these. Partial z with respect to r, well, this is, where is it? Right here. So this will be, just doing some mental math, negative sine theta over r squared. Partial r with respect to s, or actually, let me combine everything here just to avoid confusion. Times partial r with respect to s. Again, I already computed that first derivative to just be negative sine theta over r squared. And then partial r with respect to s is just going to be t. And we do the same for the other variable. So now we multiply and divide by our theta instead of our r. And this gives us, well, now this derivative will be cosine theta over r for this first term. And partial theta with respect to s is going to be 2s. And so adding up, we get that partial z with respect to r, or s, sorry, because we're calculating here with respect to s. This will be just this term plus this term. Times partial theta with respect to s, oh my god, which works out to be negative sine theta over r squared t plus cosine theta over r times 2s. And this should be good enough for an answer right here for the first partial derivative. If for some reason WebAssign does want you to express the right side in terms of t and s, then note that we just need to plug in what theta and r are given to be. So if we wanted to, we could take, where are they? R and theta, and plug them into our expression. So this would be negative sine of s squared plus t squared all over, well, r is st times t, plus cosine s squared plus t squared all over st times 2s. But I should emphasize to my students that WebAssign will likely be okay with just leaving the first terms in terms of theta and r. Okay, now let's do the other partial derivative. So now we're going to compute. So up here, what we're calculating is partial z with respect to s. Now we need to do with respect to the other variable, with respect to t now. But note that in the formula for the corresponding derivative with respect to t, the only thing that changes between these two guys is just the second partial derivatives here. We still have partial z with respect to x and partial z with respect to y, or in our case it would be partial z with respect to r and partial z with respect to theta. So there's no need to calculate those partial derivatives again. We can just do partial t, and just to emphasize this point, by the chain rule we know this will be partial z over partial r, but now partial r we differentiate with respect to t instead. And same thing, partial z over partial theta, and then partial theta we now differentiate with respect to t. But again, we know what these derivatives are. First one is just negative sine theta over r squared. And now, well, partial r with respect to t, it's not hard to see that's going to be s. So this is going to be s. And then we still have our cosine theta over r. And then partial theta with respect to t now will just be 2t. So this will be 2t. And that gives us our second partial derivative. Okay, that's it for this video. If there are any questions, please feel free to leave a comment. Otherwise, I'll see you all in the next video.